Hi. So the last video just gave you a quick overview of the synthesizer I'm currently working on. This time I thought I would share a bit more and talk about the circuits involved, starting with the power supply. Almost all analog synthesizer designs I've ever seen, they use what is called a bipolar supply. So unlike a normal power supply which has two wires coming from the main supply unit, positive voltage and ground, a bipolar supply has three wires, so positive voltage, ground and a negative voltage source. Making such a power supply isn't that complicated, especially if you plan to use a transformer and draw power from the main lines directly. However, for my design, I plan to use a USB power source, either from a regular USB port from my laptop or say a smartphone charger. So I obviously had to improvise a bit. So my plan was simple. Took 5 volts from the USB port through a DC barrel jack because, well, micro USB ports are kind of crap. Boost that voltage to about 9 volts using a standard boost converter module. I don't remember the number, I'll put it right in front. And to turn it into a kind of a bipolar supply, I planned to generate a mid-rail reference voltage using a resistor voltage divider and buffer. So you take that 9 volts, I just boosted from 5 to 9, send it to a voltage divider that gives me a 4.5 volt reference, filter it with a capacitor, buffer it with an operational amplifier, like say in my case it's the LM358. That gives you the voltage reference you need for the rest of your circuits. Now, of course, there are certain limitations. The maximum sink or source current is going to be limited to the op-amp's current sinking and sourcing capabilities. So in my case, it's going to be about 20 milliamps. But frankly, for the kind of circuits, I don't think that's going to be a problem in my synthesizer. Next, let's go to the heart of our synthesizer. That's the voltage controlled oscillator. Now, there are a bunch of controls I wanted on the VCO. First was a coarse and fine tune so that I can finally dial the pitch I want from my synthesizer. Then I wanted a frequency modulation input that would allow me to say use an external LFO or an envelope generator to produce arcade sounds and vibrato and laser sounds and drum sounds and stuff like that. And finally, I wanted a volt per octave input so that I could attach an external keyboard. This is the circuit I went with. This circuit was originally designed by Rene Schmitz. You can see it on his website. I'll put a link in the description. And it was later modified by Elliot William in his HACKADAY article. I'll put a link for that as well. Now, the original Rene Schmitz design used a bipolar supply. What Elliot William did was he modified it so that the same circuit would work, especially the exponential converter. It would work with the single pole supply, and he achieved that by adding just 2 diodes as offset voltages. This oscillator is basically a saw core oscillator. So it primarily generates a saw wave, but I also wanted a square wave. So I basically buffered the sawtooth waveform from the capacitor and sent it to a comparator. One input of the comparator is of course the saw wave. The other input is a voltage reference that we use to set the pulse width of our square wave, or what you would call the duty cycle of your square wave. Now, since we can do that, I can actually have some extra control. So I added a pulse width modulation knob, and I added a pulse width modulation input so that I could either use an LFO or an envelope to modulate the pulse width as well. Now, we have our sawtooth and square wave. I added a switch so we can select between one of these two waveforms, and then I can send this signal directly to the mixer. The only reason there is a mixer in the synthesizer is because I want to add an external input as well, say from a guitar. So for that, this is the mixer circuit. It's a very standard circuit. So you take your VCO, you send it to an attenuator to control the volume through an AC coupling capacitor, send it to an adder circuit made out of a single op-amp. For the external input, however, we need to change things a bit. Since the external input is not only a weak signal, it's also very small signal. So first things first, we buffer it. After we have buffered the signal, I sent it straight to the attenuator to control the volume. Next, I send it to a gain stage of about 10. and that output finally goes to the mixer. So pretty straightforward. Once these two signals are mixed together, they are sent to the voltage controlled filter. Now the design of this voltage controlled filter is actually a derivative of the filter used in the Korg monotron. If you ignore the first transistor and capacitor, you'll notice that this is basically a two-pole Salinki filter. You'll notice that the output of the filter is actually being fed back into the first stage of our Salinki filter. The amount of this feedback is being controlled by an attenuator, and that's our resonance control. To control the filter's cutoff frequency, I've added one potentiometer to set the default cutoff frequency, and there's an extra cutoff frequency modulation input so that you can control it with either an LFO or the envelope generator. Next, once the filtering is done, we send this signal to a voltage controlled amplifier, which is again a derivative of the Korg MS10's voltage controlled amplifier. It's practically the same circuit, just a few changes. Instead of using the resistor values they had picked, I used the ones I had available. Now, after sending the voltage controlled amplifier's output to another attenuator to control the level, that output is directly sent to our final stage where we prepare the signal to send it to headphones for two different channels, right and left. And that's basically our signal chain. The only circuits left now are the envelope generator and the LFO, that are the modulators. For the LFO design, if you search oscillator using op amp, this is the first basic design that comes up. It's basically an integrator and a Schmitt trigger connected in negative feedback, and that's our oscillator. The controls for the LFO were straightforward. You've got a rate control and a shape selection switch for triangle and square. The last circuit is the envelope generator. For that, I went with the Moritz Klein's ADSR circuit. I basically took that circuit and modified it into something like this. Now, although this circuit generates an ADSR-ish waveform, it does not have all four controls. So you have a control for the attack time, you have a control for the decay time, you have a control for the sustain value. But for the release time, the decay potentiometer itself controls the release time as well. His design has a small limitation, and that is something he has covered in his video as well. And that is for really large attack times, the envelope does not reach its maximum value before it goes into the decay phase. So I just solved that issue by adding an SR flip-flop, again made out of a 555 timer. And that's basically it for the envelope generator. And with that, I've completed all the circuits in my synthesizer. Now, all that's left is for me to print the PCBs, and that is something I'm going to cover in the next video. So till then, stay tuned for more. Thanks for watching.